Hi everyone, welcome to another Select seminar. Today we have Julio, Magdalena de la Fuente, who will be talking to us about dynamical rate reduction of Pauli measurements. So please, Julio, you can start.
Yeah, thank you for the introduction, and thank you for inviting me to present this little project I worked on last year on how to use CX to fairly easily construct so-called dynamic rate reduction schemes of Pauli measurements. So let me start by just giving a bit of context what these words mean. So Pauli measurement in quantum mechanics can be represented by a linear operator, namely a projector, that projects onto a certain eigenspace of a given Pauli operator. And we say that if it's Hermitian, we can measure it. It has two eigenvalues that can be labeled by either 0 or 1, indicated by this M here on the right. And whenever in my talk you will see like a box with like a little measurement arrow there, it represents to some projector of that form. Now, rate reduction usually refers to a term where you implement one operation on many qubits via many operations on few qubits. So you somehow have like a sort of logical operator or operation that you want to implement, and you use this in some physical system that is composed of more degrees of freedom, but then effectively on some subspace. So it acts like the same way as this high weight operation. And dynamical just refers to the fact that these smaller operations, they are composed, right? So there is some sort of time ordering, and in general, these individual OIs don't commute. So it's an intrinsically step-by-step protocol or procedure. So why do we care to implement Pauli measurements or mid-circuit Pauli measurements? There's many reasons. I would say, for example, we can use measurements to perform like efficient state preparation and manipulation. There have been like various experiments showcasing this, and one example where this like easily see is if you want to prepare the GHZ state unitarily, you need at least a circuit depth of log n, where n is like the number of qubits involved in this GHZ state. But if you have access to measurements and adaptive corrections, you can actually prepare the same state in constant depth via this sequence of measurements, where you first measure all single qubit x's and then pairwise Z operators. This will drive the state into an eigenstate of these Pauli operators, which happens to be the GHZ state up to some Pauli corrections that are also just single additional layer of gates. And this has, like, for me personally, this is very interesting in the context of preparing topologically ordered states or so on. But yeah, I don't want to talk about this today. Also, measurement-based quantum computation, of course, is like one big example where one would like to use these sorts of measurements, and depending on the scheme, they might also be like higher weight. In quantum communication, it's a very prominent thing to have. And for maybe more interesting on the application side is in active error correcting schemes. They are on the physical level usually phrased as like protocols that are only composed of measurements, where like the mantra kind of is measure all the time to drive the state into certain subspaces, but also get some syndrome information out that we use. At the end of this talk, I will touch more on the applications on this, and yeah, in many error correcting protocols, the gates that are natively available in many types of error correcting codes are actually entangling measurements instead of entangling unitaries, as you might think. So yeah, compiling these logic like measurements on the logical level into like a sequence of lower weight measurements might be helpful there as well. Okay, what's a dynamical weight reduction? In my case, 2-weight-2. So it's a special type of compilation task. In general, you want, if you have some operator O, you want to implement it, you have to compile it into whatever native gates you define. This depends on the platform you use, on the use case. Like, I don't know if you are interested in T-count, your preferred compilation is in terms of Clifford unitaries and T-gates, or like magic state injection steps or something like this. For other purposes, you might want to use different set of gates. Typical choices are like single qubit rotations around some fixed Pauli angle, state preparation, and 2-qubit or more qubit unitary gates. What I focused on in my paper is to compile these projectors that represent the effect of a measurement if you know the outcome. And the way we could decompose it is into a sequence of projectors onto other Pauli operators, P1 to Pk, where the weight of these Paulis is bounded by 2. That's what I would call a dynamical weight reduction 2-weight-2. You can, of course, also set up the same problem for arbitrary weight. But as will become clear, I think, throughout the next few slides, within the context of the X, it's particularly easy to come up with dynamical weight reduction schemes to the weight 2. This, of course, comes with overheads, like either in terms of adding auxiliary degrees of freedom, or by like increasing the circuit depth that you need. But I mean, it's more of an artifact as that you represented the projector you started with as like a black box. There's no reason to believe that just because you draw something into one box, it's actually like a elementary time step or elementary volume of whatever circuit you end up with. Weight 2, you could argue, is maybe important because for some platforms, it's believed to be a physical, reasonable native operations in like photonics or potential topological qubits, but also on the logical level of certain QC schemes. This is actually as an easy to implement logical measurement. Okay, for this, like I hope that these two introductory slides made like the setup clear and what the goal is of the rest of this talk.
Yes.
Oh, excuse me, can I ask a question?
For sure, yes, please interrupt anytime if you have questions.
Thank you. So when you are implementing the Pauli projectors with weight 2, do you have any restrictions on the adjacency of the support, or you don't care?
Well, I would say that the main result that of my paper is actually taking a desired connectivity and implementing a dynamic weight reduced scheme on that given connectivity.
So this means your compilation, in the sense that you have you start with a product of projectors and you send it to this low weight like result. You cannot do any reduction. You can only do allowed reduction.
Yeah, I mean, there are limitations. Yes, I hope they will become clear, but the construction I will show in the next 20 minutes or so, it's just takes a graph and with certain constraints that are also needed and fairly reasonable. It's like not a big restriction, but so you give me the connectivity graph and I give you a measurement schedule that implements some high weight measurements only using the via low weight measurements that only use the connectivity of this graph. Yeah, but I hope this, if you still have questions in like on that part in half an hour, please interrupt me again. But yeah, that's exactly the point, that you want to somehow introduce some connectivity constraints, understand how connectivity constraints enter the constructions of these measurement circuits. Yeah, so I will start with some general dynamical weight reductions and like examples. This will be like the first part. And then I will present the general by like identifying in this example I show, I can identify like certain mappings from like graphs. I can generalize this and will show you the main result, which is given a connectivity graph right on a DWR on that graph. And then in the end, I will comment on some aspects I didn't write up so much because it's more like a, say, collection of thoughts that I wanted to share, because I think the main message from my construction doesn't take up a full hour. So I wanted to take the additional time to contextualize the results a bit and comment on some possible applications and which which quantities to look at in which context. So I will use the X calculus in a slightly different notation than maybe most of you are used to. I apologize for that, but I didn't want to redo all the figures. I will represent these projectors onto definite measurement outcomes via small tensor networks composed of very special tensors, namely tensors in the Clifford fragment of the X calculus. There's one, say, Z tensor that I indicate with a like solid dot coming from like the delta tensor in some classical circuits where you have some control that's also represented by the same thing. And like a dual tensor thereof, which is like an X tensor, which whose matrix or whose entries are given by these numbers here. So the delta is 0 whenever its index agrees, and it's 1 if not. So the Z tensor projects onto, say, subspaces where the basis elements are the same for every leg, and the X tensor projects onto definite parity sectors of this of the bits around the tensor. As most of you probably know, these tensors fulfill very nice relations, namely, taken like an n-legged tensor, you can split it up into 2 n over 2 plus 1, or like into whatever bipartition you choose. You can split it up, and these fulfill these equations shown on the right. Now, in using these tensors, a projector onto, say, a Z to the W, like W is the weight of this Pauli operator. For simplicity, I only consider Z operators here. The projector onto a measurement outcome M is represented by this following small tensor network. You have a control tensor kind of on every horizontal qubit that participates in the measurement, and an X tensor that connects them all, where the measurement outcome is either 0 or 1, and it labels this extra tensor. Now we can use these simple rewrites to compile this ZX diagram in terms of a circuit that in this case is composed of an initialization onto some computational basis state of an extra degree of freedom that I need to add. Then I have W C naught on control X operations, and then I have a measurement outcome, a measurement onto Z with outcome M. And this would be a circuit that performs this measurement. The circuit may not be the best one, but I hope it's clear to see that you can use these rules, rewrite rules, to get a circuit. Now, the goal for us will be to rewrite this diagram differently to obtain a decomposition in terms of only weight 1 and weight 2 measurements. I will do this by post-selecting onto fixed measurement outcome, and then later calculate what happens if there's different post-selections. This can be done very nicely in like a graphical way as well. It's not so much of a problem for Pauli measurement. So yeah, the sub-diagrams we want to end up with are these four, where we have like pair measurements or projections onto the +1 eigenspace of ZZ or XX and like the single qubit analogs, which I will often represent by this splitted diagram to make it more obvious that after this measurement, this extra qubit is actually fully disentangled from the rest. So whenever we do such a DWR scheme, the compiled circuit will take up some space-time volume. So roughly, we can give that a number. If we use A auxiliary qubits and the circuit has depth D, we say the space-time volume is A times D. Of course, you can take into account like idling times and so on, but I mean, it's just a rough quantity to think about the problem. Now, if we assume that at each space-time location, at some time t, some space position x, we can only act with a single qubit, then just from the fact that we have to, and we assume that we have to like, we have to split this tensor somehow to get elementary gates, right? So just from this observation, immediately we see that since we have a degree W tensor in the middle, we need W entangling operations from the auxiliary system with the physical system, like with the qubits on which we measure. If we have like if our auxiliary system is composed of A qubits and each qubit can only act with one entangling gate, this means the depth needs to be W over A. So we immediately get like a very rough estimate that the space-time volume has to be somehow at least linear in the weight. And just as a general kind of limitation or like bound, yeah, I don't think it's too important to saturate this bound. It's just important to understand that there are trade-offs, but we will never, like there's no free lunch or anything. Okay, let me just give a first example. So a depth 5 scheme. So I will start with splitting up. So the goal of this first scheme is like to reduce the depth as much as possible. So we want to somehow put all on the vertical dimension of this diagram. And we can do this by first splitting up the X tensor into W or W minus 1, depending if the number of qubits is even or odd. Individual tensors that live like between the lines, and then we use another splitting operation to get to this diagram, which we now can interpret as like a sequence of single qubit measurements, two-body measurements, two-body measurements, single-body measurements. So we have sequences of projectors on X, on ZZ, on XX, and on Z, which, if all the measurements are +1, implement exactly this projector that we started with by construction. So as a protocol, we would say measure X on all the auxiliary qubits, measure these pairs of ZZs, whereby you pair up the auxiliary qubits 1 to 1, and then you then you measure XX between all the auxiliary qubits, and then you measure them out in the Z basis. Now this implements for all possible post-selections, this implements the measurement we want, where the measurement outcome now has to be inferred from the measurements of the individual, like the measurements that we actually did. In this case, we have to sum up all the Z measurements. And this scheme takes up, uses exactly W auxiliary qubits and in depth 5. So space-time volume is 5W. Actually, we can do much better with a different way. So we can, instead of using one auxiliary qubit per physical qubit, we can also use one auxiliary qubit per pair of physical qubits. So you see that every line of auxiliary qubits lies between two physical qubits, and at the beginning it interacts with one of the two, and then it interacts with the other one. So again, we have a protocol composed of 1 and 2 qubit measurements, and by kind of making this more mirror symmetric, like doing ZZ measurements before and after entangling the auxiliary qubits among each other, you get this slightly reduced, or you get a reduced space overhead. So in particular, you only need like roughly half of the auxiliary qubits that you used before, and you still have a constant depth scheme. So the space-time volume here now is roughly 3 times W. So far, we have I showed you examples where we have reduced the depth to a constant at the cost of adding an extensive number of auxiliary qubits. But we can also go to the other extreme. We can limit the number of auxiliary qubits. Say we want them to be constant. The smallest constant we can do with only measurements is 2. And we do this iterative splitting by first moving kind of 2 lines up. I hope it's clear that the diagrams are equivalent. And yeah, then we keep on like splitting the X tensor of high degree to the right of the diagram until we end up with like a sequence of ZZ and XX measurements that we can now interpret as a circuit. So this is like a depiction of a fully compiled DWR scheme for 2 auxiliary qubits. And this again implements this projector, and you only have to sum up all the ZZ measurements because there's no single qubit Z measurement now in this circuit. And yeah, it uses 2 auxiliary qubits, and the depth behaves a bit erratically because as you see, you always have these blocks that are composed of like an XX measurement, and then something happens, then the next XX measurement, and kind of and one auxiliary qubit always gets measured out on a single qubit basis, then initialized again, and so on, to kind of collect the necessary stabilizers that you need to have this high weight measurement. And yeah, so this, because they always come in these blocks, it's a bit of the depth like jumps in blocks of 4. But like the scaling is roughly like 4W in this case. There's of course some modifications you can do. You can like at after every XX measurement, the 2 qubits are basically the same, play the same role. So you can also switch which auxiliary qubit you measure out and which you don't. But yeah, these parameters will stay the same.
Sorry, can I ask a question?
For sure, yes.
So here it seems like the depth is 4 times the weight or the volume, but if you just had one auxiliary qubit, then it would be the same as the weight. So yeah.
Yeah, I was confused about this just a few hours ago when I looked at the slide again, because actually what I put on the right is A times D, and A is equal to 2. So you have to kind of, this cancels the 2 in the quotient in the depth. Was that your question, or?
So would this okay, maybe like I can ask, if A was equal to 1,
Yes.
The depth would be just same as the weight.
Yeah, but you can't do that with only measurements. If you only have measurements, like single qubit measurements and 2 qubit measurements, like if you're entangling operations in particular, only measurements, then the minimum number of auxiliary qubits you need is 2.
I see, because like the last circuit you have here is still, oh, it's only doing okay, it's only doing 2 weight 2 measurements and no C-naughts.
Yes, exactly. If you have C-naughts, of course, you can do this unitarily, and you would just have like a usual light cone argument that tells you can do it in W steps.
Okay, thank you.
Yeah, welcome. Okay, so let me draw these three examples on a line. We have found that there is different for different numbers of A. I have showed you like some extreme cases where interestingly you can get the same depth. I mean, the depth is the best depth you get by having like exactly W or more auxiliary qubits, but then the depth can go down to, can still be constant, namely 6 instead of 5, up to A equal W over 2. And then it goes down kind of linearly. But yeah, so you would want to maybe interpolate between these schemes as a first exercise. And we do this by drawing the way that I generalize these constructions is that I looked at the connectivity graph of the operations, and you see the general graph structure is kind of the same. You have a bipartite graph, and you kind of distribute the physical qubits that are represented by the left nodes to like the auxiliary qubits in some way. And there's no connections between the physical qubits. And yeah, so if you generalize this graph, at least, this is what you would end up with. Sorry, there is a, I just see that it should be capital A on the right. But yeah, you have like some number of auxiliary qubits and some weight, and then you distribute the edges somehow uniformly. Yeah, so what I did is you give me some graph, for example, this one, and that needs to fulfill some constraints. And namely, it has to have like the right number of vertices. Like I told you, you need at least 2 auxiliary qubits. So the number of vertices should be at least W plus 2. And the graph should admit a spanning tree with W leaves. And I call the set of leaves L. So why is this important? If you go back here and look at the example, it's kind of the way that these schemes all work is that you kind of entangle your physical qubits with some auxiliary system, each one by one, or some of them you can also do in parallel. But the point is each one individually talks to the auxiliary system. And there is no measurements you do among the physical qubits alone. Because if you would do that, then you would project them onto like some definite eigenspace, and you would not only do the measurement that you wanted to do. All the measurements that involve physical qubits have to also act on the auxiliary system. So in order to have that, like the way that does manifest in the connectivity graph is that you have the spanning tree, and like the physical qubits only live on the leaf, so on the very outside of the tree. Now, the way that I identify this graph then with like some set of qubits is that a fairly obvious way that you identify the vertices with the qubits that are used in this dynamic weight reduction. The measurements are performed on the leaves, and the auxiliary qubits are the rest. Now here I try to illustrate the construction very generally, and it works for every graph that fulfills this. So what I do is I separate the nodes of the graph in 3 subsets, the leaves, then their parents, P, and then the interior, I. At every time step, so I first start with initializing the auxiliary system. All the parents are initialized in the plus state by measuring Pauli X, for example, and the interior qubits are initialized in the Pauli Pauli Z basis, sorry, in a computational basis state. This is the first figure on the bottom left. Wait, let me see if I can. Sorry, I try to make my mouse. Somehow it doesn't show my mouse. Do you see my mouse? No. Like my cursor, do you see it?
No.
I have a question about this.
Yes, sure. Yeah, go ahead.
So if it's necessary for the connectivity graph to admit such a spanning tree, this means that the physical qubit or the data qubits are highly disconnected, right? So for computation, like gates between the data qubits, that would become super hard on a connectivity graph like that, right?
Yeah. I mean, it's a bit that you are totally right with that observation. This is only for a single single measurement, though. I'm not thinking of incorporating this in some circuit or so. I will comment on that later. But yeah, this is an important point. But in many, actually, if you actually think about like a potential physical quantum computer, the moment you have a fault-tolerant scheme, you will rarely, if not never, do gates between physical qubits directly, or data qubits, however you want to call them. You will kind of, everything you do will, or the majority of operations you do will be measurements on like a set of qubits, and then you just change the operators that you measure. These might require different connectivity, but yeah, often you don't actually perform like these gates directly. But of course, yeah, in general, depending on your application, this is of course, the case.
Do you mean in terms of MBQC, that for MBQC you would need the gates?
No.
Or what do you mean by in general for fault-tolerant?
No, like if you,
would...
I mean something, no, I mean active error correction in general. This could be a measurement-based implementation, but this could also be like a circuit-based argument. So one example to see this, if you look, for example, at the connectivity graph of Google's chips that ran the surface code experiments. It's a square graph, it's like a square lattice graph, and the qubits are on the vertices. But actually, the data qubits of the surface code are not directly connected by any couplers. The couplers are only between auxiliaries and data qubits.
Oh,
and
that's
then,
true. But still,
right,
they're all not far away. And in this kind of like tree graph, they are like super like.
I mean, that's just an example I picked here because I want to do a thing that like scales with the weight, right? Like, I mean, if you only have weight 4, then even like a tree might look close, right? So
Oh, right, makes sense. Yeah. Thanks.
it's just like you just put like a set of auxiliaries in between all the qubits that you want to act on with the measurement. Yeah, so yeah, I hope this clarified the point. Thank you for the question. Yeah, so let me try to explain this step-by-step construction a bit more carefully. We start with initializing the auxiliary qubits in step 1, and then we, at every time step, that from then on, or kind of it goes like in rounds, where at every round I measure a pair, I perform a pair measurement with a new qubit on the leaves. So in the first step, I pick a subset for every parent. I pick like one of their children that is not measured out yet, and I perform a ZZ measurement among those. This is depicted in the second picture. Then I need to, because in the ZX diagram, these filled tensors are separated via non-filled tensor. So after I've done the ZZ measurement, I have to do this XX measurement amongst the auxiliary system. This is done in the third picture. Then in the fourth picture, I can repeat this process. I measure, for every parent, I pick a leaf that has not been measured yet, do a ZZ measurement. Then I need to do a single qubit measurement and repeat this whole thing. to have the right effective CX diagram. I hope that's clear. In the paper, I give like a kind of a recipe algorithm-like thing to construct this. And yeah, there is some combinatorics if like some parents doesn't have children anymore that are not measured out yet, that are not collapsed. Yeah, you measure them in the Z basis. The other ones are measured in these X basis. But I hope, yeah, this all makes sense that, and it's hopefully also clear that these are necessary conditions on the graph. Yeah, so that's kind of the main result. And yeah, as an example, I showed this family where I just give you the family of graphs, and this defines a family of these DWR schemes, and you can easily calculate the overhead via the like average degree or something of these nodes. Okay, now are there questions for this before I go into more into the context of this all? Okay, I assume that's not the case. Not interrupt me anytime. So far, I've only talked about, well, I talked about the spanning tree being the necessary condition. And from the way it's set up, it's maybe also clear that it suffices to use a spanning tree. Like if you have a graph with some loops in it, you can also remove them and the weight reduction scheme would still work. However, there may be, that's what I want to tell you about, maybe use cases for these loops in the context of active error correction. The way you usually think of error detection in any active error correction scheme is that we use redundancies within circuits to detect certain errors. So assume you perform the same measurement twice, then you would assume that if the circuit ran as you expect, then the second measurement outcome should be totally correlated to the first one. In particular, there should be linear constraint of this form, M1 plus M2 equals 0 modulo 2. And we can actually use this constraint to detect errors. Namely, and yeah, there is a nice way to graphically represent this in the X. There's the sort of detecting regions or detector flow, Pauli webs. There's many words for it that yeah, it's not ideal, but that's how it is. And one way to get these, to derive these detectors is by like sort of finding a set of highlights of the edges in the sensor network that obey some local consistency condition. It's not too important what these rules are, but then you end up with some colorings that look like this on the right-hand side. And you end up highlighting a set of edges, a set of edges and measurements, and the measurements that are highlighted have to sum up to 0 mod 2. Now, how do we use this to detect errors? So an error, a Pauli error, is modeled by a Pauli insertion into the network. Here, instead of 1, you can think pi. It's just because I only work in multiples of pi in this, for these, like in this work, I chose 0 and 1 for convenience. And for example, if there is a Pauli error happening in between these two measurements, if it's an X error, it actually flips the constraint because the coloring rules tell you that you also have to color this value that is attached to the spider. There's of course a non-graphical way to see this as well. I just think it's very instructive to see this. And a Z error is not detected because it's not highlighted. So in other words, this constraint is not changed in the presence of this Pauli Z matrix on the bottom qubit. Yeah, so roughly speaking, you could say if my ZX diagram had some loops, there is hope to have redundancy. And actually, if you look at the protocols, measurement circuits that people propose and run in small error correcting experiments and to think of in a larger scale are full of loops. In fact, you want these highlights on the right, you want them to densely pack spacetime to detect all possible errors that could happen under a certain weight. Okay, now assume we have like a connectivity graph that we use to construct our dynamical weight reduction scheme that contains a loop. So here, for example, I showed like a small graph with 4 leaves and a loop in the middle. Now, if you recall the general construction, this triangle in the middle will be like leads to a sub-diagram that looks like this. Right at the stage where I entangle all the auxiliary qubits, this may look like this. I mean, there is also Z measurements involved and so on. It's this should just sketch the structure. And because of this diagram, we immediately see that there is some additional detector that's present. So if I add the measurement outcomes in again, represented by these 3 additional tensors, these also should be highlighted, by the way. Sorry for that. But the point is that if you run the circuit now with time going upwards, you will find that, or actually like, yeah, time runs in this depicted 3rd dimension, which is kind of upwards. Yeah, you see that you perform 3 XX measurements, but only 2 of them are independent. And this generalizes to bigger loops. It's essentially saying if you place a graph state on a ring, then you don't have to do all the entangling operations, like if you do them via measurements. The last one will be deterministic from the other ones. Now, these detectors, since these are XX measurements, they detect Z errors. In particular, Z errors don't actually change the value of the projector that or like the measurement outcome that we get. So they are not annihilated by this projector, they just commute with it. So these detectors won't be useful to protect the measurement that's implemented by this measurement sequence itself. It could, however, still be useful within a bigger quantum error correcting circuit where it influences the way that other measurements detect errors. So schematically, this should not be taken too literally. It's just if you have 2 detecting regions that overlap on a subsystem, now this blue detecting region, it kind of has to, like this is now a black box, and this we compiled somehow in terms of the ZX diagram. Now this blue coloring, like this indicating which how like Pauli's propagate through the circuit, this can move through, like this has to move through the circuit element somehow and then goes out again. This is kind of what's indicated by these colorings. And now if we change, like if we add one of these loops in the dynamical weight reduction scheme that implements, say, the central measurement where these 2 colorings overlap, then this loop changes how these so-called flows or Pauli webs, they move through this compiled circuit. So this is all just to say that we don't know yet how these additional redundancies within readout circuits influence the error correction property, because it highly depends from the context. In general, though, one can say that this could act like a flag, like an additional classical bit that I would get out of my circuit to tell me a bit more about errors. Okay, so in the last 10 minutes, I want to zoom out a bit more and think about more general, like if you have now a circuit composed of many measurements, how much does it tell me that there is like a space-time volume associated to a single measurement of a certain weight? You could think naively, well, okay, if I have a single dWr with space-time volume v, then, well, if I do n of them, I have space-time volume n times v. But that's actually not true, and it's far from that. Even in like in some unitary circuits, people know how to interleave and effectively parallelize these circuits. Because the moment you compile these in terms of like lower weight gates, suddenly there is room in between for these qubits to actually already encounter the gates that they need for the next effective gate. So graphically, somehow you can imagine tilting these in space-time. So in the end, they take up a bit less volume, and on average, you end up with a lower space-time volume per dWr. There's different trade-offs you can think about. Roughly, if you have a large number of ancillas, then you can have a very short time per dWr. I mean, I told you that there's a space-time overhead is kind of bounded from below, but if you have more auxiliaries, this allows you to have a shorter depth. However, in this low depth regime, like most of the physical qubits interact with the auxiliary system at any time. So there's not much room for parallelization there, but you are done quicker in a way. But if you have a small number of auxiliary systems, then there is room for parallelization because more qubits idle. So an extreme case would be the example on the right, where you see that actually for a single physical qubit that participates in the measurement, it only has one ZZ measurement, and then it does nothing for like an extensive amount of time, extensive in the weight of the measurement that I introduced. So after that, it could already participate in the next measurement, which you can, for example, think of this diagonal placement, these gates diagonally in spacetime. Yeah, this is just some food for thought that I wanted to put out there. One last thing, sorry. These different types of implementing these high weight measurements by many low weight measurements actually leads to some generalized notion of hook errors, which just means the way that Pauli errors are equivalent within a circuit, right? So you can take a Pauli insertion and you can use the X rules to like move it around the circuit, and they are all equivalent. If it's a unitary circuit, then this is a deterministic thing, like because a unitary maps a Pauli to a unique Pauli, like a Clifford unitary at least. If you have measurements, there is ambiguity to which Pauli it gets mapped to. Essentially, there is like a larger space of equivalences. And this leads to this more generalized hook errors, and we don't really understand so far how to treat these in a more general setting. There is I think the like work by Ben and others on distance preserving readwills does a good job in that direction to understand how different ways of compiling measurement circuits with other measurements lead to like some different effective behavior of errors, but we are far from understanding this. And especially in this interleaving setting, where in the unitary case makes a big difference how you interleave. It doesn't seem to be so obvious how this plays out in the measurement case. This paper I showed here, like from October 2 years ago, is from Microsoft. They do it for a very specific code for like surface code based QC, but I would like to see some more general treatment of this. Okay, so let me conclude. Yeah.
First of all, thanks for shouting out our paper. I have a question about this comment on hook errors, just to understand. Is this related to this temporal shifting, or is this more general observation independent of this temporal shift?
Could you explain shortly what you mean by temporal shift?
The saying above, this parallelizing where you're shifting the measurement in time.
Yes.
I guess. Is this because it's on this particular slide? Is it related to the hook errors, or are the hook errors?
It's so the reason I put it on this slide is that in the unitary case, different ways to interleave even though they agree on the error-free realization, might lead to very different circuits in the non-error-free case. Now, like it's a problem that in the unitary compilation setting is mostly important. Like the hook errors are mostly important when looking at interleaving things. So I put it on this slide, but it's also, it should also be considered, I think, within a single measurement block.
Yeah, because like,
I think that's mostly what you did, I guess.
yeah. No, but I have some, maybe, yeah, we should discuss this at some other point, but I have some ideas.
Yeah, I would be. That's cool.
But when I'm in Berlin. Yeah.
It's good. Yeah, so let me just conclude. Yeah, so the main result of this paper is constructing a DWR from of weight 2 from a given connectivity graph. This leads to very naturally leads to a family from like increasing number of auxiliary qubits, effectively not caring about connectivity, but just using this construction as a helping tool to construct these circuits by just taking a graph, a bipartite graph with some auxiliaries and some physical qubits. So I showed you how just following this procedure leads to like how loops in this graph manifest in terms of the resulting ZX diagram and how this could be helpful for QEC applications, leading into looking at how these dynamical weight reduction schemes play out in context when you do it for many measurements that are like consecutive measurements. There's different trade-offs depending on the application you have in mind. For error correction, you may want to get like the syndromes at a high enough rate, so the depth shouldn't be so big. Whereas for actual computation purposes, when doing like a logical compilation, compressing runtime might actually be beneficial if like it's fairly cheap to add a few extra qubits, if this allows you to trim down like the full runtime. So I want to hint at some related work and open questions. There is, of course, I only told you about a dynamic weight reduction to weight 2. You can, of course, think of other weights that are bigger. It's not obvious to me how to play the same games that I was able to play with these graphs because, yeah, just the way that higher weight measurements are represented in the X not as easy as like weight 2. In weight 2, it's just like an edge connecting two tensors, and then you can easily get like a post-selected diagram and lift it to a diagram where you add new measurements in. Like this reinterpretation is very simple. There is a paper that also uses graph theoretic tools to come up with subsystem codes from potentially non-local stabilizer codes called wire codes by Neuden and Dom. They construct subsystem codes whose so-called gauge group is generated by operators of maximum weight 3, and they write down a measurement schedule for the stabilizers, which boils down to, in my language, to a DWR of weight 3. So it would be interesting to contrast the constructions and compare overheads that you like, how they differ and what do you get out. Then there is the paper from Ben and company that I hinted at that formalizes distance preservation in the context of DWR2 for QC protocols. There, the big question I see is that like combining kind of the concepts at least to also incorporate connectivity constraints, incorporate like decoding constraints that you might have on the classical data that you get out of your circuit. Yeah, these are all, I think, interesting questions. What is largely lacking, though, in the current literature is the flexibility that you sometimes have that we, for example, explored in this Locaifying the color code paper together with Alex and Marcus some years ago, where so there are certain error correcting protocols that, when written as a tensor network, can be have a sort of topological symmetry in this, and that means that you can actually choose your time direction arbitrarily. So in particular, you can think of cutting the diagram into equal time slices. Usually, if you have a circuit, this is given. You say this is time 1, 2, 3, and so on. But for these topological protocols, you can choose the time direction freely, and this actually gives you a lot of flexibility when coming up with new error correcting protocols. And even though you can argue very nicely about macroscopic QEC properties when doing these deformations of these diagrams in order to get circuits that traverse this diagram in a different time direction, it's not straightforward to do some more lower level statements about these reinterpretations and different time directions. For example, how important is distance preservation? Like, can you, or like just do, I don't know, is there something to be gained if you look at a full circuit instead of its individual components when compiling? Phrased in this way, it seems like there is, but it's not obvious to me, at least, how to tackle this problem practically. More generally, there may be like a use case in noise reduction schemes that are based on teleportation, just because teleportation is something that uses measurements. And the paper that I put there on the low left has a scheme that is based on measuring potentially high weight stabilizers. And since they make statements about effective error rates when propagating errors through all these measurements and so on, would be interesting to see how these error mitigation techniques in the end perform when you compile the measurements differently. With this, I want to thank you for the attention. Unfortunately, I don't have a thank you slide. I forgot it. Sorry for that. I hope it was interesting. I'm happy to take any questions, discuss further things. Thank you.
Okay, thank you very much, Julio, for the nice talk. Already answering several of our questions. Let me maybe kick it off with a question before the audience maybe thinks of some others. So you mentioned like you can make an arbitrary connectivity graph, but you were mostly considering, I think, the case where you have a Pauli weight measurement where all the qubits are involved, but you could also have a relatively low weight measurement that's spread out across all the qubits. For instance, if you do a measurement in some low density non-local code, right? Have you
Yes.
cases where you have like a long distance in between and you still try to like prevent getting too many ancillas? Because if you have a lot of measurements for many qubits, it might take a lot of time to make them be close to each other.
I think that's a good question because it's it's not clear how to do this with what I told you. One comment, though, just to clarify, is that I looked at the graphs that only involve the qubits that are participating in a single measurement, right? So you were, I think, already thinking of like on one larger scale where you have like a circuit of many measurements. I was only looking at a single component, like a single measurement. But there, I think there's no way to get like if you are limited by spatial connectivity, there is some constraints on also the sort of space-time volume you need. You can do it in constant depth if you allow for like an extensive number of ancillas. Like instead of moving the ancilla there, you can also have many more in an entangled state. It's actually a trick that Craig Gidney and his collaborator used in this recent one-dimensional memory paper that they put out like 2 months ago or something. There they use this trick that they have qubits on a line. And I mean, the concept generalizes. You have some qubits on the line, and then you say every other qubit is just an auxiliary qubit, and I repetitively entangle them in some graph state. Whenever there's space in my circuit, then I do that. And then I can use this as a resource to perform high weight measurements in constant time, given that resource. And if you look at the circuit here on the right, it's actually doing something similar, like the leftmost example. If you flip or it actually does exactly that. Like if you flip the time, like if you read it from right to left, it first prepares an entangled state of the auxiliaries and then measures in constant time.
Okay. Are there any other questions in the audience? So looking around. Yeah.
Hi, thank you so much for the talk. It's very interesting. I wonder, so you talk about this space-time overhead, which is very similar to Daniel Lintinsky quantify the resources in the active volume architecture. And I'm curious, like, have you thought about, like, given different families of Hamiltonians, maybe you'll have different, like this space-time balance so that you can give different optimization strategies to do this dynamic polyproduct decomposition.
What do you mean with Hamiltonian?
Like,
is that, yeah.
For example, like Hamiltonian for different purposes, or like basically different quantum algorithms, like algorithms.
I see. Yeah, I think there's a lot of room for improvement, or like for further study in that context. This fits into this logical compilation question. And yeah, one thing that I could maybe say is that I mean, I don't work on this myself, but I know that large classes of quantum algorithms, especially variational ones, they use like Pauli rotations, right? There's like some theta parameter in your circuit, and this actually tells you by how much do I have to rotate in like some around like a Pauli axis that is determined by some product of Paulis, right? So it's not a single qubit rotation, but like a many body rotation. For example, because that's a term that happens to be in your Hamiltonian that you want to simulate, and then just like a parameter you want to find its ground state, whatever. Now you can use these measurements to do gate teleportation, essentially. So instead of unitarily applying the rotation, you can prepare an extra resource state, like an auxiliary state, in an sort of in an of a state where this rotation was applied to, and then you can use this high weight measurement to inject this gate instead of doing it unitarily. So in this way, you could also use these schemes to directly get like constant depth or different size depth schemes that implement this Pauli rotation that you, I think, need in many algorithms, variational algorithms, that is. But I've not looked into this at all in terms of like actual numbers or something. But I think to make the point, I think ZX is the right tool to look at this.
Another follow-up question about your previous slides is you compare large A versus small a, and you said when A is small, there are a lot of idle qubits. Yes, I wonder, is it possible to like reuse those idle qubits, like for like then in that case, what would be like? Do you need to kind of like have a sliding window protocol or something that kind of track the lifetime of a qubit so that you can allocate smartly?
On the last one, I don't know, but I have to say that I should add that these idling qubits are actually physical qubits, right? So if you look at the circuit on the right, on the bottom right, then the top two qubits are the auxiliary qubits. And they don't actually idle much at all. What idles is the physical qubits. And I mean, these should be, if you actually think of running the circuit, they should be stable, right? So either they are like error-corrected qubits, or this is like all short enough within all the coherence lifetimes. But yeah, in other schemes, depending on the geometry of your graph, you might also end up with long idling times for the auxiliary qubits. And I think there you can optimize a lot if you have more restrictions on your graph, right? If you look at, if this graph here, wait, here. If this graph has like a hub, like a few parents have like just 2 children, and there is one that has like is connected to many, then of course this one node, this one parent that would be connected to many would be the bottleneck.
Right.
And the other ones, they would just sit there and do nothing. So you can probably use them for something else after having measured them out or something. So yeah, but this highly then depends on what graphs you consider and how. Yeah.
So can I understand that if you're looking at the physical qubits, even if they're not used, but they're still participating in the computation, so they're still storing the information, we cannot read
Yes.
for auxiliary.
Yes.
So it's just about how we use those qubits, the auxiliary ones.
Exactly. So yeah, and I mean, it's very easy to see from the ZX diagram after you have, right? So after each single qubit measurement, the way I represented it is literally by splitting the diagram. So you directly see that this qubit doesn't participate anymore. And so then after that, you can just, yeah, use it for something else exactly.
Right. I also had a question. Because like your constructions, they are like post-selected diagrams. But is it clear
Yes.
to get the other outcome, you can always push this Pauli into the future of the circuit onto the data wires? Or,
Yes. Yes. Yeah, there's a few arguments how to see this.
This is only without noise, right? With noise, it's not.
yeah, I'm just thinking.
Yeah.
Yeah.
Yeah, that's true. Yeah. So so for Pauli measurements, it's easy to because every Pauli projector just splits your Hilbert space into 2. Right? It's like 1 + 1 and 1 - 1 outcome, and they have the same dimension. It's easy to come up, like to find the unitary that maps from one to the other. And then you can just add like this Pauli matrix, which is just a collection of pi spiders, and we'll find that it's pushed through. In the presence of errors, of course, these circuits differ. Yeah, and it's not, I think that Ben's paper does a better job in dealing with that, actually.
Consider
So let me just put it up.
if you push it out, it might become a high weight correction. So that is
Exactly.
actually corresponds to many Pauli corrections. So a single measurement corresponds to many Pauli corrections. So if that measurement is faulty for some reason, you actually introduce.
Yeah. Yeah, you could, yeah.
Yeah.
Yeah, but in principle, also this interleaving question goes in that direction, that at least in the unitary case, it's really about the circuits differ in the presence of errors. But without errors, the circuits should be the same, because I mean they should implement the same thing on the logical level. So yes.